I'm a big fan of superhero films, and one of my earliest film memories is of watching the old Superman films starring Christopher Reeve. Now, you might be thinking, what on earth has this got to do with chemistry? Well, in order to find out the answer to that, you're just going to have to keep on listening. I'm Mr. Lee, and welcome to another episode of Chemistry Revision Stories. Before we get on with today's episode, let's recap the homework questions from last week. The first question that we had was, what element is able to displace chlorine? And now remember, because the reactivity of group 7 decreases down the group, only elements above it will be able to displace it. So the only element above chlorine is fluorine. The second question was, what will the products be when chlorine reacts with sodium bromide? Now, because the chlorine is more reactive, it is able to displace the bromide ions. So all we do is a switcheroo. We swap the places of the chlorine, the bromine, and so it will make sodium chloride and bromine. And the final question was, why do group 7 elements decrease in reactivity as we move down the group? And it all links into the electron structure again. So as we move down the group, the outer electron shell is getting further and further away from the nucleus. So it is becoming less and less attracted to the nucleus. And because group 7 need to gain one electron when they react, it becomes harder and harder and harder for the elements to gain that electron as you move down the group. That's why they get less reactive. Let's crack on with the episode, and our story today starts with my film memory. In one of these Superman films, you see Superman in his fortress of solitude, and he's fallen in love with Lois Lane and wants to propose to Lois. And of course, when you make a proposal, you've got to have a fancy ring, but there are no ring shops near the fortress of solitude. So what does Superman do? Well, he finds a bit of coal that for some reason he has lying around in the Fortress of Solitude, and using his super strength, he squeezes and squeezes and squeezes, and he compresses that coal, and out of it he gets a tiny diamond, and he then uses his heat vision to attach that to a ring and proposes to Lois Lane, who of course says yes. So what has that got to do with chemistry? Well, today we are going to be talking about the chemistry of carbon. That means, of course, our element of the episode is going to be carbon today. So let's start off with the basics. Its atomic number is 6, so that means it has 6 protons in its nucleus, and that means it also has 6 electrons. Its atomic mass is 12. Now that's the most abundant form of carbon, but it does have isotopes which are incredibly important in a whole range of different fields, in particularly for carbon dating. So we can actually look at the ratio of different isotopes of carbon and use that to work out how old organic matter is, which is absolutely amazing. I've mentioned that it has 6 electrons. In our standard electron configurations that we need to know for GCSE, that means it has 2 in its first shell and it can have 4 in its second shell. And crucially, those 4 electrons are all unpaired, which means it can make 4 covalent bonds to other atoms. Let's just remind ourselves for a moment what happens with a covalent bond. So in a covalent bond, we have unpaired electrons, and these can be shared between 2 non-metal atoms. And as they are being shared, both electrons in this bond are equally attracted to both of the positive nuclei. And that attraction is really, really strong. So these covalent bonds are incredibly strong, and it requires a lot of energy to break them. Because carbon is able to make these 4 bonds, it means it's one of the most versatile elements that we see in the world around us, because it can bond with a whole host of other elements in a whole host of different ways. So that is why it is the backbone of all organic molecules. People often to refer to humans and life on Earth as carbon-based life forms. That is because our carbohydrates, our proteins, loads of other organic molecules have carbon at their base because it is capable of making these 4 covalent bonds. Let's think now about some of those structures that I mentioned earlier. Let's take diamond. So diamond is a really pure form of carbon. So it's just made of carbon atoms. And so if we take one carbon atom, it's able to make 4 bonds. So it has 4 other carbons bonded around it. And each of those 4 carbons can bond onto an extra 3 other carbons. Each of those can bond onto another 3 carbons. Each of those carbons can bond onto another 3. Each of those can bond onto another 3. So very, very quickly, we can grow this molecule into what we call a giant network. And it has this really, really rigid structure because all these carbons are bonded to each other, and they're bonded with these very, very strong covalent bonds, which requires a lot of energy to overcome if we're trying to heat it up. But it also makes diamond one of the hardest substances that we know of as well, because these strong covalent bonds and the regular pattern of the giant structure means that it is very, very difficult to shift these atoms. But carbon can also bond in a few different forms as well that we need to be aware of. Often it is based around a hexagonal structure. So sometimes carbon will make 3 bonds and it will be bonded to other carbons, and its 4th electron, instead of making a 4th bond, becomes delocalized. So in graphite we have hexagonal rings of carbons making 3 bonds to each other. The 4th electron is delocalized, and so we get a layer of hexagons making a layer of graphite, and we have multiple layers that build up to make graphite. And because we've got this delocalized electron that is able to flow through the layers, in between the layers, graphite is one of the few non-metals that is able to conduct electricity. We can also take a single layer of that graphite, and that's what we call graphene. Graphene itself can also conduct electricity because it's got a delocalized electron from each of the carbons, so that can flow above or below the layer. And for its width, it is very, very strong. It was discovered back in 2004, actually, in a UK-based university, and it was sort of hailed at the time as a miracle material, and it has some applications. It perhaps hasn't had as wide a ranging applications as people first thought, but it's found a lot these days in running trainers, and they have these layers of graphene built into the soles of running trainers, and it just helps keep them more durable and make them last a little bit longer. So picturing that single layer of graphene, if you were to roll it around in on itself, you would get a tube, and we'd call this a nanotube, sometimes called a fullerene. And these fullerenes, again, have a very, very high, what we call tensile strength. That means they can withstand sort of pulling and straining, a lot of tension going through them. And they can also be used to deliver medicines on a really, really tiny scale, because these nanotubes are just made of a few hundred atoms. Similarly, if we were to roll those hexagons around into a ball, which usually contains 60 carbon atoms, and we often call it a buckyball, that can be used as a cage to hold a particular molecule, or it can be used as a lubricant, because lots of those little balls can roll over each other, making the substance very, very slippy. So those are just a few examples of the different forms of carbon that you need to be aware about for your GCSEs, and you need to understand how the uses of them are slightly different. So far, those have all been examples of what we would call giant structures. So diamond, graphite, graphene, the nanotubes and the buckyballs are giant structures, but carbon can also form what we call simple molecular structures as well. The most common one that you'll have heard of is carbon dioxide, where we just have one carbon atom bonded to two oxygen atoms. Now, those covalent bonds are very, very strong, but when we think about a property such as the boiling point or melting point of a substance, it doesn't just apply to one molecule, it applies to a whole host of molecules, what we call a bulk property. So if we imagine we've got loads and loads of carbon dioxide molecules, when we are boiling it, we are separating out those carbon dioxide molecules. We're not actually having to break those strong covalent bonds. Another example of a simple covalent molecule involving carbon is methane. So one carbon, and then you have the four hydrogens are bonded to the four unpaired electrons. Again, when methane turns into a gas, we are not breaking apart the carbon and the hydrogen atoms. All we are doing is we are separating separate, discrete methane molecules. When we're looking at these molecules then, what attraction are we having to overcome? Well, it's the attraction between molecules. And for these simple covalent molecules, that attraction between them is very weak. And so it doesn't require much energy to overcome that attraction. And therefore, as simple covalent molecules like carbon dioxide, like methane, they have very low melting and boiling points compared to our giant covalent structures involving carbon, like our diamond and our graphite, which have strong covalent bonds. They don't have any intermolecular forces at all, just the strong covalent bonds, and that requires a lot of energy to overcome. There we have our key carbon structures that we need to know about for GCSE. We've covered a lot of ground there quite quickly, so it's really important that you go back over the key features of the different forms of carbon. But one thing I want to leave you with is just the understanding of how versatile, how varied carbon can be in the world around us. And without it, we wouldn't be here. So let me leave you with 3 more homework questions for next time. Firstly, how many bonds do carbon atoms make? Next, is diamond a simple molecular structure or a giant network? And then finally, why does carbon dioxide have a low boiling point? That's all from me. Tune in next time for another episode of Chemistry Revision Stories. Bye for now.